Hi. It's the first time I come to a talk where there's beer right outside the door, so feel free. Hi, my name is Derek, and I'm happy to be here to share my insights about Bluetooth security with you. In this talk, we're going to talk about what Bluetooth security really means in the industry, their security designs, real-world constraints when we're building Bluetooth in your next IoT product or project, and the pragmatic choices you're going to have to make. So heads up, it's going to be a choice between being pragmatic and a choice between being very secure about what you deliver, okay? So I'd like to go over a quick intro about myself. So my name is Derek. I am currently a principal security consultant in Zühlke. Here you can find my contact email and LinkedIn profile. I actually started here 10 years ago as a master's student at ETH, so it means a lot coming back here. I later did my doctoral studies, also in computer science, and my specialization, I don't know if you guys still have it here, is information security. So afterwards, I joined ABB as a scientist in cybersecurity, and then later on as a security engineer and security architect. Okay, and since last year, things were changing up a little bit, and I thought to change my career, and that's why I ended up joining Zühlke as a security consultant. Okay, so I think being on two sides of the aisle, whereas at ABB you have a product to develop, you're a product company, and at Zühlke you're a software service company. We're not like Der-Yeuan, for example, where they have their own products. Oftentimes, I think the mentality is different between these two sets of companies. And I think the findings, the experiences that I have, that would be the most valuable thing. So maybe not necessarily about Bluetooth security today. Okay, so we'll talk about that as we go throughout the talk. Okay, so the agenda today is roughly the following. I want to talk about Bluetooth IoT applications and attacks. We're going to talk about what Bluetooth standards have built in as security mechanisms for us. We're going to talk about real-world design constraints when you actually are using Bluetooth as an interface in designing your next IoT product. And finally, we're going to talk about your design choices, compromises you're going to have to make, and enhancements you're going to have to make as well. Okay, so let's have a running example for the rest of this discussion. First, let's talk about Bluetooth and IoT, an example. So we're talking about roughly, let's say, a simple Bluetooth IoT device. Let's say it's a bit more critical. It's in the health sector, so probably like a pacemaker or like a health monitor on a patient. Right? And nowadays, since it's Bluetooth, the reason you have Bluetooth most oftentimes is because you want this connectivity, right? So you want to connect it to something, and typically that would be an application, right? So you have this application where you can configure the monitor and you can read some measurements, right? So it's all passive at this stage. Now, when it comes to industrial settings, oftentimes having an app on the phone is not enough. In the industry that I was working with before, oftentimes we're dealing with, let's say, a hospital or a factory that's manufacturing some things. And these health monitors are not just monitoring people, they're monitoring your machinery, your assets, your motors, and your production line. And so you can't really always have your service engineer walk around the factory floor to read all the measurements. It simply doesn't scale. And so eventually you're going to have some, in addition to the user modifying the app, using the app, there will always going to be some gateway on site where you fetch measurements and you can send that to the cloud, okay? And at the end of the day, you have some domain expert, maybe a doctor, maybe some machine specialist that can analyze the data and give you advice. Of course, you have some AI in the cloud. That's what everybody strives to do. So in this trend of becoming data-driven companies, Bluetooth plays an important role here as the final mile where data is exchanged between your endpoints. Now, the reason we don't use Wi-Fi or Ethernet is naturally because of constraints such as battery constraints, power constraints because they got to be really small, or even connectivity itself, they got to be installed far away in remote areas where there may not be good connectivity. Okay, so there are a lot of design constraints, and let's quickly do a little threat modeling here. Oh, by the way, we do threat modeling, and I'm assuming that you have a basic understanding by taking similar information security courses in the past. So let's do a little threat modeling, and the first step that you want to understand is what is at stake here. What are the assets that you want to protect in this setting from an adversarial influence? So you might have customer data. That's very important, given the recent trends in data breaches and the such. You would also have things like operational configurations, so you want your configurations to work correctly, right? And you would also want to have to protect your intellectual property, because maybe you're running some local configurations, local algorithms on Health Monitor. And this is what the buzzword currently is when it comes to edge computing, right? So you don't want your competitors to buy one of your devices and steal your algorithms therein. There might be other things such as other connected assets in your environment. So not only do we care about the asset we're adding to a customer's site, let's say in a factory or somebody's homes, we also don't want them to become the next treadstone for future attacks. For example, if an attacker is able to compromise this device, they may be able to scan other Bluetooth devices and do a sort of a lateral move to other devices that can attack them. All right, so in this talk, we're going to mainly be talking about the attacker that's on the Bluetooth channel. So we're not going to talk about other parts just yet. Now, the good news is there's a lot of Bluetooth security features that's out there with improvements from version 1.0 all the way to the latest, I think, 5.1 and so forth. The bad news is most of the things that I'm going to talk to you about today have been broken in the past, if not on the protocol design level, then on the implementation level. So that's very bad news. And a lot of the research, a lot of the attacks discovered were also, let's say, research that's uncovered at ETH and even at EPFL. So these are closely relevant attacks that would affect the normal operations of Bluetooth. So one can already say with increasingly popularity of people researching into these security protocols that Bluetooth seems like a lost cause. Lost cause in the sense that it may not even be worth the while to secure it if there's so many attacks going on. And some of it date back as May this year. Okay. All right, so the main thing here is that that doesn't stop companies from using it for the many benefits that Bluetooth brings. Based on recent studies, companies know that IoT is at risk. So 71%, of interviewed executives still believe that they should go for IoT setups. And oftentimes, the last mile, you have your Bluetooth settings, you have your Bluetooth devices. Most of them understand that there is risk of IT security and data leakage, but they still go for it. So here you go. The main takeaway I have for showing you this is that we cannot be confident about Bluetooth security. However, on the business model, there really is, in general, not so much awareness on the technical seriousness of these security loopholes, such that companies are still going for these innovations. They want simply to be relevant still in the market. Right? Any questions or objections so far from the audience? Okay, good. You all look like you want to perform surgery on me later on, so I'll try to keep it light. Okay, so the main thing, when you read into the many news articles that I've shown you before, the main thing at the end of the article is the suggestions from the researchers or the white hats. What they tell you is typically the following things. Turn off Bluetooth when you're not using it, or patch it up. Right? So by turning off Bluetooth when you're not using it, this relates more to the end user, to you guys, to the customers of these IoT builders. Right? I personally think it's very user-friendly. Whenever you ever turn off Bluetooth on your device, when you turn it off, you're going to notice that a bunch of apps are going to give you warnings that your IoT is not connected anymore. Regarding to patching, that has historically been a pain point for industries. We're talking about traditionally mechanical or engineering companies who don't have a lot of software expertise. So probably they buy a software chip containing Bluetooth stack off the market. They use that SDK for that version and they never move on. So they don't even have this update process. So the question becomes, well, can we do more here than doing something that's either user-friendly or that's unrealistic for the world, right? And the problem is, should we do more? Should we keep ensuring the security of this Bluetooth channel? And my main understanding here is probably it's time to look for a different direction. Okay, so to get into more technical detail, because I think most of the audience here might be a bit technical, we're going to talk about two variants of Bluetooth technology. You might have heard of it already before. One is called Bluetooth Classic. So this is often referred to as basic rate, enhanced data rate, BR/EDR. So these are your wireless headsets. Okay. And the other is Bluetooth Low Energy. This is more often used in industry now. So it's used for low power consumption devices and is often referred as LE, BLE, or in rare cases, Bluetooth Smart. This is new, and that will be the main technical content for the talk today, okay? The main reason is this old one is quite insecure as we know it, and there are a lot of security improvements in the new one. Okay, so let's walk you through a simple communication workflow for Bluetooth Low Energy. So first we have, again, this health monitor that we mentioned before, monitoring humans or machines, probably. And you have this app or a gateway, right? So first, you have your Bluetooth devices advertising, we all know that. And then the device noticing this advertising packet would then initiate a request. In this request, the device is going to enumerate this Bluetooth device, sort of like when you plug in your USB into your laptop then understands what interfaces there are. Right? So in Bluetooth, these are called services and characteristics. There are different types of services, such as environmental sensing here, that has two characteristics of this Bluetooth device that you can get, for example, temperature and humidity of the environment or of the patient. Right? This is oftentimes probably considered low criticality, so it's okay to leave them open. Another service that I use here as an example is the maintenance service, and that can consist of two characteristics or two interfaces, so to speak, where you can send firmware updates and you can read the logs, or you can program the logs. These are typically more critical, and so you want to protect them more. When it comes to protection, what kind of security features are we talking about? What kind of security properties? All right, I can imagine that most of you are thinking of the CIA principles, so confidentiality, integrity, and availability, right? Oftentimes, integrity is replaced nowadays with authenticity. Right? So yes, to have these secure channels set up, you need to have some keys. And the main point here for later communication is to have a secure key for secure communication. Okay, so there's going to be plain text communication, as we mentioned before, on open ports or these plain text services, kind of like port 80. And then there's going to be secure connection for this maintenance characteristic. What it does, what the Bluetooth protocol says, is you need to perform these pairing or bonding, right? Pairing is you exchange a key, and bonding is both parties remembering that key for the future session, kind of like TLS resume. Okay, so after exchanging that key through whatever way we're going to discuss later on, they're going to do secure communication. This is where they do, I think, AES-CCM, so an authenticated encryption mechanism that ensures the message level confidentiality, integrity, and authenticity all at the same time, right? So this is actually quite good practice. It's not the strongest crypto, but it's quite good already. So here I have no complaints. Any questions so far? All right, so the typical goals here is that we want to have confidentiality, integrity, and availability is something that we don't really address here because you sort of assume that when they're connected, they're available. Right? Okay, so let's talk about the pairing mode. So the pairing mode is where security matters the most. Has anybody developed security or Bluetooth security protocols in the past or used Bluetooth in your IoT projects? Show of hands. You have, right? Cool. So we have some, but has anybody used some form of set up a secure server before, like web server, email server at home? Yeah, I see a few more hands. So it's all quite basic. It's two parties remotely not knowing their identities, and they want to verify them, right? In the case of Bluetooth, it's about understanding what you want to protect, understanding whether or not the two devices are belonging to the same user, right? So there are many protocols out there. Many ways of pairing it. First, you have the most insecure one, legacy pairing, where you type in the pins, right? And the second one is and they've made an improvement where you have something called secure simple pairing, where you have some mechanism called JustWorks, where they automatically exchange a key for later use. They have other mechanisms like Numeric Comparison, Passkey Entry, and out of band. The same goes for further improvements on Bluetooth Low Energy. So that's what they do here as well. You have also the similar variants. And also with LE secure connections, this is the most secure one. You also have the similar modes of association. So they really care about whether or not two devices, when they're connecting, it's actually perceived as the same thing by the user that's doing it. That's the main important thing. We're going to talk about this one today. So let's just go over legacy pairing. We'll see how insecure it is in a nutshell. So legacy pairing here is a device connecting to a user connecting to a device, and the user types in the PIN, right? And then the user also goes to the other side of the other device, and types in the other PIN. And what it does is the protocol checks whether or not these two pins are an exact match. If they are a match, they would use what's so-called a password authenticated key exchange, so PAKE, to establish a secure channel, a secure key for the channel. This has been broken because typically people use 0000 as their PIN. Just works is something that just works. There's no interaction required. The device can automatically connect to another device, and they will do an authenticated Diffie-Hellman key exchange to set up a shared key between the two devices. This is secure against secure against an eavesdropping attacker, so they will not be able to obtain the key. Cryptographic details we leave for another day. Okay. All right. So there's no interaction required at all, and that's the beauty of it. Right. You don't need any interaction. We'll see its limitations later on. Numeric comparison is something similar to PIN entry. So here, the device actually generates and displays a number. Also, the other device also generates and displays another number when they're connected, and then the user just has to compare whether or not the pins are the same. If they are the same, they click OK, then the devices will pair. Passkey entry is the last one that's related to pins or passwords. And here in this case, the user would actually type in the device will generate and display a key, and it's up to the user to type it in on the other side. And if it's the same, then it matches. The last two relates very similar to when you plug in your Chromecast at home, right? And when you pair it up, you have this 4-digit or 4 alphanumeric units that you need to verify. All right, the final one, which is the most secure one, is called out-of-band. So out-of-band pairing is a mechanism where you don't really pair in band, you don't really exchange the key material in band. You use another mechanism, for example, an NFC touch. That's the only example mentioned in the Bluetooth specification, whereas, for example, I would take my phone and tap it on, let's say, this Bluetooth device, and it's through the NFC interface that they exchange the key material later on used for their secure communication. So this is considered the most secure one of all the variants, based on my opinion and understanding. So here is a quick summary of all of the mechanisms you see out here. Right? So you have the different mechanisms now in different color coding. Just works is automatable. It just works. There's no user interaction required, but there's no authentication. There's basically no user there to check that these two devices are the same devices they want to pair. And for the other ones under blue, they provide some form of authentication, and green provides the strongest authentication. Okay, the thing here is, if you look into all the news articles or snapshots I've shown you before, almost all of these association methods have been broken in the past, be it on the protocol level or on the implementation level. Let's say weak randomness, or simply the protocol is just information theoretically broken. So this is the first issue I find personally with the many more secure, more authenticated pairing mechanisms in Bluetooth. The second thing I find is the following. So it's not like you have these 4 options and then you can immediately use them in your next Bluetooth project. There are also constraints on your Bluetooth devices. For example, you need to have some I/O and proper display on the device. Now, when it comes to a medical device or like a machinery measurement sensor, where I was working on intensively in my former employer, these devices typically don't have a keyboard, not even a button. They don't have a display, right? So in this case, when it comes to that, most of our IoT devices that are in the industry do not have I/O, and the only mechanism that Bluetooth supports would be just works, unauthenticated, vulnerable to man-in-the-middle attacks, active attackers. All right, so what do we do here? So to summarize, there are a lot of real-world constraints when it comes to Bluetooth. So first, you have the usability aspect. Whenever the user needs to click a button, that's another burden. Whenever you want a user to type in a PIN, that's yet another burden. So the user wants things to be as streamlined as much as possible. So we're talking about, let's say, factory workers who might have, feature phones, or who are not so apt in the awareness of cybersecurity. Right. So other things that you need to consider in the real world when you develop products is also compatibility. So there's many vendors for these Bluetooth gateways out there nowadays. I think the major one would be one from HP. It's called a Aruba gateway. You might see that already in restaurants when you have your serving staff using like an iPad to order stuff. There are many gateway versions out there in the factory floors, and they come with every different types of Bluetooth versions. Some might even support only up to 4.2, which is probably not the most secure, but some might support only up to 4.1. So there's many limitations here. The other one is that there's a lot of legacy security, legacy products in your, be it on the app side and on the device side. Okay. So finally, there's also physical constraints. So for example, even if you want to do NFC pairing, out-of-band pairing, the device might be very much out of range when you want to actually pair it. So you might have different commissioning processes for your product. There might be an engineer installing in a shaft that's very hard to get to. Now, how do you really pair with that remotely? So based on all the real-world constraints, the question that I often have to answer to my stakeholders when I'm delivering on a project is, well, how do we address Bluetooth security in IoT, right? Derek, you've told me about so much insecurity in Bluetooth, about the so many security features in Bluetooth and the many constraints, right? What do I do? Right, so when we are faced with these choices, typically we have to balance between being secure and providing customers with the top value on security quality, but on the other hand, being very cost sensitive and being pragmatic about our choices. So all of you have seen now the basic fundamentals of how Bluetooth would pair, about their usability, and have an idea of how insecure they are in the real world. Give it a thought of how you would proceed with this problem, okay? All right, so the first thing I would do in my past projects, I have never gone beyond just works. I've always used at most just works, at most. Oftentimes, it's even an open connection without any encryption. So one of the benefits of just works compared to all the other solutions is that you can automate it from gateways, from phones, from your app, and as such. And the second is that there's no interaction required on the device side. It just has to send out advertising packets, and you connect it, right? So we understand that JustWorks does an unauthenticated Diffie-Hellman key exchange. If you know what that means, you know it's not secure against an active attacker, right? But in this case, this is the most compromised, the most often seen compromise I've made when it comes to discussing with stakeholders on what security features to prioritize. It's transparent to the user because the user does not have to perform any numeric comparisons, right? Finally, it offers some basic protection. So typically, in product development, they have a list of security features. They just want things to be encrypted, right? And in this case, it is encrypted. Yes, with a key that's vulnerable to an active attack, but still encrypted. It doesn't, we know this, it doesn't provide security against a meta-level attack. Please.
But only during pairing, right?
Yes.
After pairing, this is totally fine.
Exactly. After pairing, it is still fine, yes.
But you can also like unpair, force them to become unpaired and to pair again.
Yes. Mm-hmm. You can trick phones to unpair and pair again. Yes. You can intercept the channel next time they come and pretend that you don't really remember this bond, right? So there are many attacks on this, right?
It's not just during pairing, you can force.
Yes. Yes. Mm-hmm. So there are, I think both of you mentioned these. This attack window is a problem of attack window, right? When an attack is reasonable, right? All right. So this is the first step I implement for our customers typically, and in an agile way, when they implement security in the next step, that's where we do more. And this is typically where they stop on the communication channel security, at least using Bluetooth. The other thing, when it comes to sensitive data, so for example, medical data or regulatory protected data, when it comes to user privacy, is that customers would often end up developing their own secure channel. So what it means is that, well, devices would still advertise, they would still design it this way, the phone would still connect, you would do a simple JustWorks pairing, as I mentioned before, but on top of that, they would do a TLS handshake. They actually implement a TLS handshake on top of that secure channel. So they treat JustWorks as something on the side, right? And after that, you get a TLS shared key, and then you can perform secure connection, secure communication. Okay. Now here, there's a lot of implications here. First of all, well, it means you need to maintain a PKI for the certificates on the client side and on the server side. Now think about how much process that would add to a traditional engineering company who don't even know about PKI and that they're commissioning their device, which is supposed to be in the factory for about 20 years, right? So this is the first hurdle you have to get across. The second part is, well, you'll need to deploy the certificates to the device. Do you deploy it during commissioning or do you deploy it during manufacturing, right? These are two different design choices you need to make. The final thing, which I think is the benefit, is that what you're saying here is that we don't trust Bluetooth at all, not even just works, and we implement our own state-of-the-art secure connections using the best-in-class industry standard in TLS, right? So you're really treating Bluetooth as just an adversarial channel. So that's what I like about it. All right, another thing I often see with our customers is that they oftentimes have IoT devices that have different levels of access, right? So oftentimes you might have the doctor accessing this medical device so that they can configure it, and the patient might only be able to read the data instead of configuring it at all, right? So you have the device establishing a secure channel, as I mentioned before, using TLS or its variants. You run some authentication protocol, maybe using some challenge response, zero knowledge proofs and such, if you want to be very, very critical. And then here you can do some access control based on some authorization rules, right? So the user will have some credentials even on the device themselves, right? Okay, so this is one thing that I often see, and we have implemented for some customers using some simple role-based access control. But even then, it's already quite complicated. All right, another topic that I see customers do is that maybe they don't want to have an end-to-end TLS channel on their secure communication over Bluetooth, but they will implement some end-to-end encryption for critical data. I remember before, the secure channel exists only between the health monitor here and the gateway, right? That's where the gateway would decrypt all the data and get access to the plain text information. For some of the implementations that I have developed recently, we actually designed it such that the health monitor would encrypt the data using, for example, the public key of the cloud, right? And they would send it over through the two chains, so either through the gateway or through the app to the cloud, and it's the cloud that's doing the decryption. At the end of the day, the gateway is the gateway is just again just part of the channel, right? So this is really about reducing the trusted computing base. And the user would have to use their app to authenticate to the cloud, where it would also check for authorization rules and get the data. This is another pattern that we have been seeing. Okay, and then that's what the user does. So another thing that I think is important here is to look beyond communication channels, but really look at the application logic. So we should really thoroughly test the Bluetooth application logic. This is an example that's done, again, by university, but it's very realistic because the guy made quite a cool video about it. Basically, they're hacking the firmware update mechanisms of Tesla so that they can upload malicious firmware. There was actually a missing verification step in Tesla's key fob. And this allowed them to access the secure elements and extract the secret keys that's necessary to start the car remotely without the key fob anymore, and allows the attacker to drive away. So that's the last advice that I am giving to the audience here, that you should always properly check your application logic. The final thought I have for everyone here is that, well, when it comes to security, in my line of work, when we're dealing with developing products in a rapid cycle, we don't always have the time to develop all the security requirements in the beginning, right? So as shown in the previous talk about the tug of war between Agile and Waterfall, oftentimes companies are stuck between doing something that they refer to as water, scrum, fall. So they're doing Waterfall, but in between Waterfalls, they're doing things in an Agile way. So what it means is that everything needs to be pragmatic, although the security requirements probably needs to be designed earlier. But what we've talked about so far today is that Bluetooth security only addresses attacker on the last mile, right? So it could be that the attacker is everywhere. The attacker could attack your cloud. That's the biggest attack surface because anybody can connect to it. The attacker could be on site and connect to the gateway and attack it. This could be a corporate attacker that has access to their corporate channel where the gateway is installed. The attacker could also attack the user's phones through social engineering. And finally, the attacker could also perform phishing attacks or any other attack on the individual domain expert. So there's a lot of other attacks here that are, let's say, more likely, more scalable, that it deserves more of our attention. So at the end of the day, when it comes to Bluetooth security, I typically present those different layers of access control mechanisms, and we see, based on the product owner and the customer, where they want to go. All right, so the main takeaway is to be pragmatic and to really understand the implications so that you can defend your security design choices in these projects. I'm open to questions. Thank you.
Where you mostly implied that you want to protect the data. Do you have any advice for protecting the denial of service?
Denial of service attacks, right? So often, I have, but it's mostly heuristics based, because the most common denial of service attacks that I can think of is on an asset, and that's on the availability, right? So let's say the operational functions of this health monitor. I can think of ways where I could just connect repetitively to this health monitor and drain its battery. That's one of the main attacks I often see, or repeatedly connect to it so that it cannot receive connections from other places. This is, I think, I only have partial solutions for it, such as rejecting connections, having some rate limiting there, and some heuristics or whitelisting on MAC addresses. But even then, I'm sure the audience can think of ways to spoof MAC addresses. Right? Limited. Any other insights or your opinions in your own projects? Please.
How can we secure the traffic for, like we talked about health monitor, which I guess is non-critical. But let's say we're talking about a pacemaker or something that has more effect on someone's health. Then we obviously really don't want to use unauthenticated Der-Yeuan, and we can't really push a button or input a pin. Like, are there other ideas for how can we communicate to the device? And yeah, given that, let's say we can, then maybe it works in Switzerland, but now I'm on holidays somewhere different, and they don't have the correct certificate, the medical staff, and it's just scary.
Yeah.
Are there ideas for that?
Yes, and I have, I think, some past experiences when I was studying here, and we were discussing the same very topic in conferences and in coffee chats. So if you're mentioning like certificates, unauthenticated DP-Helminki exchange, I suspect you would understand the basic mechanisms of authentication, right? So oftentimes, yes, you can implement some authentication mechanism between, let's say, a pacemaker. But when it comes to emergency services, so that's to defend against attacks, and that would be fairly secure. But across countries, if you take a ski trip in the States and you get into an accident, and the emergency services crew don't have the private key or the public key certified, then they can't do anything. In the real world, what they do is they would electrocute you with a little bump, and then that would disable the pacemaker completely, so they just work around the pacemaker. In real-world critical conditions for these implants, that's what they do. So they simply work around it, and they install their own, for example. Yeah. So it's a little bit like working around the problem. Yeah. Thanks for your input.
If there are no more questions,
yeah.
Thank you very much for your great presentation.
Thank you.